Hello, class. Today, my group and I will be discussing vibrations, more specifically, vibrations of a beam and the many properties of vibrations that make it such an important topic in structures. My name is Andrew Watson, and I will be introducing this experiment. First, we fixed one end of the beam, and on the other, the beam was free. Then, we shook the beam, and using sensors pointed directly at the free end of the beam, we measured the back and forth distance of the beam, which are vibrations. Now, during this experiment, our actual objectives were to determine the first three natural frequencies of the beam, the nodes and antinodes, as well as the final damping behavior. In order to do this, we used certain equations and our raw data from the experiment to derive the values desired in our objectives and to demonstrate the effect of vibrations on a beam. Also, you can see the dimensions of the beam we used during the experiment, as well as other constants needed for these equations. Now, I'll hand it over to Gabby to explain the procedure and what exactly we did during the experiment. Thank you.
Hi, my name is Gabby, and I'm going to be talking to you guys about the procedure part of our experiment. To start off, this photo shows the setup we used. The main part was the beam, which was made out of aluminum, and it was fixed to the table at one end and free at the other end. At the fixed end, there was a shaker, which was used to shake and vibrate the beam, and there were also accelerometers at both ends of the beam, which is a tool that can measure how much the beam is vibrating. We also used a laser, and this shines onto the beam with a red dot shown and gets reflected back. And then sensors can measure how much the beam is moving at that specific point. All of these tools were connected to cables so that these signals could be sent to our computer for us to look at. There were two ways we could excite and shake the beam. The first was using white noise, which is a mixture of many frequencies over a wide range. Using white noise lets the beam respond to all of its natural frequencies so that we could then find the resonance frequencies where the beam was moving the most. And then the second method is just setting one frequency to test the beam at. And using this, we tested the resonance frequencies that we found using the white noise method from before. There were a few more important tools we needed to do this. The first tool is on the left. It's called a function generator, and this is what we use to set one frequency to test the beam at. In the middle is called an oscilloscope, and it has a screen that shows the vibration signal, which let us see how strong the vibrations were. And on the right, these tools are called amplifiers. And basically the signals going in and out of the beam were very small. So we needed the amplifiers to make the signals bigger so that they could actually shake the beam and that we could actually read the signals when we got them back. This video just shows how the beam shook at one of its resonance frequencies where the movement was the largest. And now I'm going to pass it on to Joe to talk about our results.
Thank you, Gabby, for talking about how we ran through this experiment. I'm Joe, and I will now talk about what we got from doing this experiment and what exactly that means. So we need to calculate the second moment of inertia, which is taken from the width and thickness of the beam, which was measured with a caliper, which is a more precise measuring tool. And then we input the all the constants as well as the variables that we obtained physically for this experiment into the equation that I know Andrew talked about earlier, and I'm just reinstating, and where the beta values are obtained from multiplying the coefficients times the length of the beam, which is 43.5 centimeters, with the first coefficient being 1.88 for the first frequency, 4.69 for the second, and 7.85 for the third. Here is a crude drawing of the experimental setup with the holder that made the beam cantilevered, making it fixed on one end, free on the other, with the laser tip accelerometer measuring the vibrations on the tip, here with the red dot, and where the natural frequencies were calculated as 13 hertz for the first one, 81 for the second, and 226 for the third. Next, the beam was first, the three theoretical plots were made and graphed here with the theoretical antinodes, which are where there are peaks and valleys shown with the blue and the green, blue and the purple ones for the theoretical and experimental, which the theoretical are the calculated ones that and the ones that are seen on this graph, and just the nodes, which are where the graphs cross the x-axis or where there's zero movement on the beam, which are shown through the red for theoretical and the green for the experimental. The third frequency was seen to be the most consistent and with the overlapping theoretical and the experimental for both anti and experimental nodes. And the values shown for the theoretical are shown in this graph, not graph table, as well as the observed ones, which were derived from us running the experiment itself. Next, we had the machine run white noise to just vibrate the beam at not specific, at certain hertz ranges based off of our theoretically and calculated versions that we used, in which whenever there's no tip mass added to the beam, they are shown in this top graph with the peaks representing the natural frequencies. And for the second one, it might be hard to decipher which one is the second natural frequency, where that is decided through the highest peak, while the one on the left and the right of this highest peak is the local maximums. The peaks are representing, yeah, as I said, the natural frequencies with the labeled values shown with the red dots and the numbers right above them. The frequencies were then plotted. This is for the beam without a tip mass because we don't have theoretical calculations for a beam with an added tip mass at the end, where the calculated ones are further reinstated here at the top. Then with the laser measurement of the laser tip beam at the laser at the tip, and then just like the measurement from the white noise machine running, in which the first natural frequency had the most error, while the third had the least error, which was seen in that previous graph, with the third frequency having the most overlapping theoretical and experimental nodes and antinodes, while the first was pretty skewed in where one node was compared to the next. And this is due to the impact of the damping ratio of the beam that is just installed with the boundary conditions of the beam, which are just like what the beam is and how it reacts to different things. Next is the comparing the beam with the beam that has the added tip mass, where yet again the first natural frequency is shown to have the most variation, while this time actually the second beam is the most consistent throughout the whole experiment. And this further reinstates that impact of the damping ratio since there's a percent change through the laser decelerometer or the laser tip beam measurements of 9.091, while the white noise had 0, which is very vast, while the third is pretty consistent within like a similar range, and the second is exactly consistent between the two. And you heard me talking so much about damping ratio. What is that? That is just how much the beam like starts to slow down, like what affects the beam slowing down after it's been vibrating for a while. And that is gone from the equation shown on the screen, where y1 is the leftmost peak, and then y2 is the one directly to the right of that, which is seen here. And then you plug that into the equation below that, which is zeta, to find the actual damping ratio. Now I want you to figure out the second damping ratio. Let's call this first peak to be 0.039, my bad. And then the second one to be 0.036. Pause this video, try to find it out for yourself, and then I will talk more about what I got. Okay, hopefully you pause that. Now, the damping ratio I got, and hopefully you should be around this area of 0.0072, showing a higher damping ratio with whenever the tip beam is added, tip mass is added compared to no tip, which supports the hypothesis that I was claiming earlier with the damping ratio being more and showing more variation between the beam with the tip mass and the beam alone. Thank you for listening to me talk about the results and discussion. I will now pass it to Robert to talk about the conclusion and wrap all this presentation up.
Hello, my name is Robert, and I'll be concluding this presentation by restating the experimental objectives and how well we achieved them, foremost meaningful things we learned, difficulties encountered in the experiment, experimental repeatability, and suggestions for future work. The three primary objectives for this lab, as stated, were to determine the first three natural frequencies, determine nodes and antinodes, and the damping behavior. These values were all successfully found in the experiment, and thus we had a very high rate of success. The first three frequencies were found to be 12, 82, and 223 Hz, which is just a unit that says how many vibrations the beam cycles per second. We also learned that there are nodes at 21.5, 34.5, and 37.5 centimeters from the root. We also found the antinodes at 12.5, 17.75, and 30.5 centimeters from the root. The damping ratio was found to be 0.00705. This is a unitless quantity just to tell us how quickly the beam slows down its vibrations after we let go. Now, although the experiment was a success, we had some challenges, including using the oscilloscope to zoom in to view our waves. It was hard because we had to move the dial ourselves by hand, and it was very difficult to get the picture to fit right as we were changing the frequency. It was also very difficult to read the distance of the laser from the beam root by holding up a ruler to it. So some ways to improve our experiment for next time to resolve these issues would be to perform a slow motion sweep using a computer. This way the computer can move the frequency 0.01 hertz at a time, which helps us find the sweet spot better than our shaky hands could. We could also attach a lightweight adhesive measuring tape directly to the side of the beam. That way the ruler would vibrate with the beam, and we wouldn't have to worry about the gap between the ruler and the beam, which can cause a measurement error called parallax, which occurs when you move your head around and then you're trying to measure something isn't directly on it. So the results, also we found that the results of this experiment are likely to be highly repeatable. This means if we tried it again with the same experiment later, we would almost certainly get the same results. This is because the beam's favorite frequencies change with the material and shape. So if we stay the same material and shape, and we use the same laser and shaker, then the physics of this experiment will stay true each time. So this concludes our experiment presentation. Thank you so much for staying with us as we explored the world of vibrations.